Welcome everyone to today's lecture. Last week we completed our discussion of portfolio optimization, and we looked at a very practical example in which we used data from the German stock exchange, and we optimized the portfolio. We saw that actually when you use a number of simulated random portfolios, you are not getting close to the efficient frontier of portfolios. Especially if you ban short selling. If you don't allow short selling, you can see that actually most of the portfolios you get, even if you optimize it, the optimal portfolio will not be on the efficient frontier. That only happens as soon as you allow short sales. And you can actually, with this real data, you can generate the same plots as those that I've shown you before in our discussion of Markowitz's portfolio theory. Okay. Now the next chapter is on asset models, and more precisely one should say asset pricing models and assumptions for the time evolution of asset prices. And as you can see, we start with the Wiener process and stochastic integration and stochastic processes, and this whole chapter is basically about stochastic processes. I'll take it very slowly here because I know that most of you have never seen a stochastic process before and are not familiar with stochastic integration and the Ito, the lemma of Ito, especially jump processes. But if you take your time and you take it slowly, I think you can understand the basics of stochastic processes and why these are the most important models that are being used in financial mathematics for modeling asset prices. You can read about this in almost any textbook on financial stochastics and financial mathematics. It's also included in the investment and Risiko management textbook by Albrecht Maurer, and here you have the related pages for this. Now, where do we start? To start in asset pricing, we need to think about how we want to model asset prices. We have to start with asset prices and later on move on to returns, but we start with asset prices, and asset prices being the prices of stocks, bonds, derivatives, and whatever. At this point, we don't really care about what types of asset we are looking at, but usually we assume that we are looking at stock prices. So we want to model stock prices. And in statistics or probability theory, the most common model for such a process is a so-called stochastic process. And what is a stochastic process? A stochastic process is just a set of random variables. Now, usually you would assume that you have a random variable x, and x is maybe distributed according to a normal distribution, and x is our stochastic model for a stock price. However, stock prices change over time, so that we don't actually have one random variable, but we have a set of random variables, and the set is indexed by an index t being larger than 0, and starting with a 0. Now, why do we need a set of random variables? Because the stochastic behavior of these asset prices could change from one day to the next day. So we don't actually have one, let me just get something to write here. We don't just have a normal distribution like this, and this distribution remains constant from today to tomorrow and to the day after tomorrow, but it might be that it actually changes, that we have maybe a 0.1, 1, and then we have a different, maybe a t distribution with nu being 10, and so on, and the distribution and the random variables change. And this is why in a stochastic process we don't use just one random variable for the whole set of prices, what we have a set of random variables xt, and the distribution of xt might remain constant, but it could also change. And this is why we need a stochastic process. And a stochastic process is just this, a set of random variables. And we, of course, always interpret this usually as a time series. That is, the index indicates a point in time. This is why we've already chosen the index to be t like it's in time. Now, in many cases, we have, of course, the idea that prices change in discrete time. However, from a modeling standpoint, it's more easier and also more sensible to look at time-continuous processes. What does it mean? The difference between a discrete stochastic process and a continuous stochastic process is just that in the discrete case, the index set is discrete, so it's finite. You have t equal to 1, equal to t equal to 2, 3, 4, maybe up until 5. In the case of a continuous stochastic process, this index t is an element of the real numbers. So you have infinite random variables. And this makes sense because changes in time take place not just from today to tomorrow, but prices change from now to the next hour, now to the next half hour, next 10 minutes, next 5 minutes, and in intraday frequency, and now in intraday high frequency trading, prices may already change after just a couple of seconds. So it makes sense for the index set to be infinite. And the simplest and easiest example of a stochastic process is a so-called Wiener process. And we'll see that in just a bit. What is a Wiener process, or as we also call it, a Brownian motion? A stochastic process, remember, this is a set of random variables, is called a Wiener process or a Brownian motion if the following three properties are fulfilled. First one is the increments, the increases from one point to the next point. So xt1 minus xt0, xt2 minus xt1, and so on. All those increments are stochastically independent for all indexes. What does it mean? The change in the process, the change in the price from one point to the next, and this increment in time being infinitely small. This increment is independent from the next increment and from the next, and so on. So even if we know that the prices changed by, let's say, 5% from yesterday to today, this information is of no value to us. This increase we have, or the decrease today to the next point in time, is independent from all the changes we've seen before, and is independent from all future changes. So increments are stochastically independent. Next, the distribution of the increments, xt plus h minus xt, only depends on this lag h and not on the position. Meaning, I need to write a little bit. Imagine you're looking at the increment from, this is quite difficult without the pad, from t0 to t1. Then the distribution of these changes only depends on the length of this period h. And if we are looking at the same increment at a different point in time, it has the same distribution. However, if we suddenly are looking at an increment over 2 periods, then this increment has a different, or might have a different distribution. But the increments, the distributions of the increments are just depending on the lag h and not on the position in time. And in addition, the increments are normally distributed with xt minus xs being distributed according to a normal distribution with mu times t minus s and sigma squared times t minus s. So you can see that the mean and the variance of the normal distribution is depending on the lag t minus s. So it could be one day, 1 hour, 1 second. And we call mu times t minus s the drift, and sigma squared times t minus s the so-called diffusion of the process. So what is a Wiener process or a Brownian motion? Sounds tricky, sounds difficult, but actually it's quite simple. It's just not one random variable that is normally distributed. It's a huge, infinite number of random variables, and 3 properties have to be fulfilled. The increments are independent. The distribution of the increment only depends on the lag, and the increments are normally distributed with a certain mean and a certain variance. Why is mu and sigma s called the drift and the diffusion? Well, you don't have one variance and one mean. But as you can see, the variances and the means of all those random variables, they are driven by these parameters mu, t minus s, and sigma squared times t minus s. So both parameters seem to govern and seem to drive the means and the variances that might change during the process. They are not constant, but you actually have a good idea how these means and variances are driven by mu and by sigma s. So these are called the drift and the diffusion because they more or less drive the process in its mean and its variance. And that's a Brownian motion. Why it's called a Brownian motion? It comes from mathematical physics, and in mathematical physics, a Brownian motion, this model is the model for, I think the motion of molecules. And actually, most of the models we'll be seeing today, they come from mathematical physics, and these are all models for some kind of physical behavior. For example, we have the heat equation. The heat equation shows how heat is transferred through a rod of steel or a rod of metal. So you take a rod of steel, for example, large piece of metal, you heat it at one side, and heat goes through the piece of metal, and it walks. Oh, that's another great word. The piece of metal slowly heats up, and in physics you want to describe how heat is transferred through this piece of metal, and this is the heat equation. Actually, this is also a so-called diffusion process. A diffusion process explains how one material is, I don't know actually the verb in English. In German it's diffundieren. How it might be diffuses, how the diffusion takes place from one material in another. So if you take, for example, a bottle of oil and you throw it into a bottle or a bag of water or a canister of water, you want to know how this second material is distributed in this first material. And this is the diffusion process, how diffusion takes place. So the Wiener process, Brownian motion, is actually quite simple, and this is closely related to a random walk. What is a random walk? A random walk is actually a stochastic process with, again, independent increments and changes.
Excuse me.
Yeah?
Just like, don't get it wrong. So, for instance, the stock price of Daimler.
Yeah.
We are observing it at one day and at the second day, and the distributions could be different.
Yeah. The distribution of each random variable could be different. Not completely different, because as you can see, we are imposing this assumption and this restriction on the process that the legs are normally distributed. So this assumption that the increments are normally distributed puts certain restrictions on the distribution of xt itself. Yeah? So you will not expect xt to be t normally Pareto Clayton Pareto normal distributed. So it's likely that the xt's are also close to a normal distribution. Actually, I don't think that you can prove that. I would have to look that up. I only know that by definition the increments are normally distributed. Yeah? But it's probable that the xt are also normally distributed or close to a normal distribution. But you're right, the xt's, the prices, if you like, they are not identically distributed. Okay. Now, the Wiener process can also be written in the following notation. xt is equal to w0 plus mu times t plus sigma times square root of t times zt, with zt being a standard normal distribution. And in this case, you can see how actually this process works. The price xt is given by a constant w0 plus the drift times the time index plus the volatility or the diffusion times square root of the time times a standard normal distribution. And this shows you that actually this is a very simple process which, if you have a closer look at this definition, is governed by a constant plus a deterministic constant, well, it's not a constant but a deterministic term, plus a constant plus the square root of time, which is again deterministic, and only zt is stochastic. And this is important because you already know a standard normal distribution. And here you simply take a number of constant parameters. You take the time index, let's say t equal to 1, t equal to 2, t equal to 3, and so on. But remember that t is known. You know t. And you know that if you are in discrete time, that if you are at t3, t4 will be next. So it's not stochastic. And the only thing that introduces a random behavior is just the standard normal distribution. So this is a very simple stochastic process. And actually, there is even a more simpler stochastic process. You might have seen this. Let me write this down. It's easier. This is an even simpler stochastic process. This is an AR, an autoregressive process of order 1. What is an autoregressive process? It is simply a process in which the value of the process today is yesterday's value, slightly changed, plus some noise. This epsilon is a random variable. It could be a standard normal distribution. Usually you assume so-called standard white noise process. And the idea is just that you take yesterday's value, you multiply it with a constant parameter, let's say 1.1, and then you just throw in some random white noise, some random behavior that is very standard. And this is an AR1 process, an autoregressive process of order 1. Meaning that, for example, you take, what is a good example for an AR1 process? Let's say the number of customers on a Monday in the perfume store. Why? It is probably related to last week's number of customers. It will probably increase or decrease by a certain parameter. Let's say they usually, from week to week, they have about 1% more customers, for whatever reason. So it's last week's value, xt minus 1, times 1.01, 101%, plus a little bit of random behavior. Might be a little bit lower, might be a little bit higher, but there is just a little bit of random white noise inserted via epsilon t. And here it's more or less the same. You simply take the constant parameter w plus the drift, which is the general trend, which is upward or downward or constant, depending on time, and then you take a parameter sigma, and you multiply sigma with the random noise inserted into the process by zt. So this is another way of writing this Wiener process. We know that the covariance between 2 points in time is the minimum of s and t times sigma squared, so you can see that the diffusion parameter obviously drives not just the variance but also the covariance. And then you have the mean of xt is w0 plus mu times t, and the standard deviation is sigma times the square root of t. And again, you see mu and sigma, those two parameters are driving the mean and the variance, but they are not exactly equal to the mean and variance. And this is why you don't simply just say mean and variance of the process, but you call it drift and diffusion. Drift meaning the trend, which is, of course, related to the mean, and the diffusion meaning the way and the volatility of the process. And this might change. If you make it even more simple, if you take W0 equal to 0, the drift to be equal to 0, the volatility of the process to be equal to 1, you can see then actually xt is equal to square root of t times the standard normal distribution. Meaning, if you have no drift, mu equal to 0, if you have unit volatility, the distribution of xt is just a simple standard normal distribution times the square root of t. So you can see, although a Brownian motion, a Wiener process sounds quite difficult, in the case of a standard Wiener process, this is just the dynamic version of a standard normal distribution. Dynamic because we do have square root of xt in here. Yeah? So, and this is important because remember that t increases. T is equal to 1, et is equal to 2. So even in this case, the distributions are not constant, they are not identical, but they change slightly because we are multiplying the standard normal distribution by a square root of t. Okay, now to make it a little bit more intuitive, let's go to MATLAB and let's simulate a path of a Wiener process. And what is a path? A path is actually, if you take, well, you can look at a stochastic process in different ways. Assume that you have a stochastic process that describes a number of throws of a dice. You take a dice and you throw it 1,000 times, then you get a stochastic process. In this case, if it's the same dice, of course, the process is stationary. The random variables will be exactly identically distributed. And you can now look at two different things. The first thing you can look at is just taking one random variable and look at it over time. And you can also look at this process in the cross-section. Now a path is a look at one of those random is a look at the process over time. And we want to simulate this here. And we start by setting the random number generator to its default state. This is the first line. Then we have t equal to 1, n equal to 500, dt is equal to t over n. And please remember from now on that dt is always supposed to be the difference in time, the increment in time. So every time you see something with a dt, dx, this is meant to be the change, the differential in the process, or the differential in time. Why don't we write it with t minus 1 or something like that, or xt minus 1? Well, remember that in many cases we are looking at discrete or continuous processes. And it's just easier to write, to leave out all those differences and to just write dt, meaning this is the infinitely small change in time. In this case, of course, it's discrete, so it's t over n, so it's 1 over 500, so this is the increment. So we are going from 1 to 500 in steps of 1 and 2 and so on. dw is just a vector of zeros, w is a vector of zeros, and now we take what? The change in the Wiener process is square root of dt times rand n. Rand n is a random number generator simulated for the normal distribution, that is why it's rand n for normal distribution. w1 is just this value. I have to mention one thing. For this to work, you always need a starting point. You always need a point at which you want the process to start, because you've seen that the information on the process is just about the increments. So you know how the process changes from this point to the next point, but you still need to determine a starting value. And we do this in line 6, and we just say W1, the first point of W of the Wiener process is just this dW. And then for all points in time 2 until n, the change in the process is square root of dt times rand n, and W is the jth value. The jth value is the j minus 1th value plus the change. So you just reverse engineer the idea that dw is wj minus 1, and you simply turn it around. You can see that if you subtract wj minus 1, you would get dw, the change in the process, is equal to wj minus 1. Is that clear? The process and the definitions I've given you show you what dw, the change in the process, is. So we know the change, and we start here. This is wj minus 1, and we simply add wj, and we get wj. So wj is given by the previous value plus the change. Previous value plus the change. And so you construct the next value and the next and the next of the process. And this is actually very similar to a random walk. And it actually, I have to look up, I think it's the random walk. What is a random walk? A random walk is the idea that you have a process, you start somewhere, and you pick, for example, in 2 dimensions, you pick a direction that is random, and you pick a step length that is also random. So, for example, I would start here, I would choose this direction and a random step length, then I'm here. Then, same thing. I choose a random direction and I walk here. It's called a random walk, or also sometimes a drunkard's walk, because it looks pretty much like the walk of a drunken person. This is a random walk, and this is the same idea here, and the same process, more or less. You have a starting point, you calculate the increment, the change, and in fact you've seen that the increments are independent, so it's regardless of where you walked in the step before. I now choose a direction here, and this increment is normally distributed. Again, another direction. Here it's just a little bit different because it's in one dimension. I can only go up or down. If I would do it in 2 dimensions, I could go, well, I could choose a new direction in the plane. I could walk like this and this. This is the path of a Wiener process, and you will see on the next slide that this is what it looks like. You start, actually, I started somewhere above 0, I think, or might also have been 0. And each change now, each increment is independent from the previous ones and normally distributed with certain parameters. Let's look which parameters I chose. Well, it's a standard Wiener process. There are actually no... You can see that I'm using rand n, which is a standard normal distribution, and I'm simply taking square root of dt times the standard normal distribution, so it's a standard Wiener process. I could change it, I could include a drift and a diffusion. It would only change the general trend, and the volatility of the process would be higher or lower. But, quite interestingly, if I had shown you this plot, and hadn't told you that this is a Wiener process, and I had told you, well, this is the DAX, or the S&P 500, you would have believed it. And this is why, at some point, mathematicians had the idea, well, actually, those stock prices pretty much look like a standard Wiener process or a Wiener process. Okay, so we do have a very simple model for a stochastic process that seems to be, well, at least reminiscent of a stock price evolution. Okay. One thing one needs to remember is those paths of a Wiener process, they are continuous, but they are nowhere differential. Stetig, aber nirgendwo differenzierbar. And why is that? Quite simple. You do know what continuous means and what differential means. In layman's terms, it means a function is continuous if it is connected, if all points are connected, and it's differentiable if it's smooth, if it doesn't have sudden breakpoints where there's if it's smooth enough. And actually, the path of the Wiener process is a very trivial, well, not actually trivial, but a pathological example of a function that is continuous everywhere, but nowhere differentiable. And this is something, for example, math students learn in the introduction to calculus in their first year, that there are some functions that are continuous everywhere, but not differentiable anywhere. And how does it work? It works like this. Actually, the process is just a huge number of little steps, up and down, up and down. And again, remember, the Wiener process, the Brownian motion, is continuous. So what happens is that if you only look at some points, it will look like this. You can see that all points are connected, but here and here the function is differentiable because it's a linear function, but it's not differentiable in this point, because there you have a sudden change in the function and it's not smooth. In German, the Knickstelle. Now, the stochastic process is continuous, meaning that you don't actually have 1, 2, 3, 4 points, but actually it is much more and much smaller. And in fact, those changes decrease infinitely, and in the end, you only have an infinite number of those points at which the function is not differentiable. Is that clear? Maybe I'll explain it in German. Might be a little bit easier. Die Funktion ist überall stetig, weil alle Punkte natürlich miteinander verknüpft sind und sie letztlich eigentlich nur aus linearen geraden Stücken besteht. Aber im Grenzwert, dadurch, dass wir hier uns in stetiger Zeit befinden und die Anzahl der Punkte letztlich gegen unendlich geht, haben Sie am Ende nur noch eine einzige Aneinanderreihung von Knickstellen. Und im Grenzwert gegen unendlich sind es nur noch Knickstellen. Und damit ist die Funktion überall stetig, aber nirgendwo differenzierbar. Ist nicht konstruiert, aber es ist schon ein pathologisches Beispiel, ja, weil man das irgendwie so gewohnt ist, gerade aus der Schule, dass man sehr viele Funktionen hat, die sind stetig und an manchen Stellen nicht differenzierbar. Wenn eine Funktion differenzierbar ist, ist es zwangsläufig auch stetig, aber das ist so ein klassisches Beispiel für eine Funktion, die eben einen Extremfall darstellt. Überall stetig, aber nirgendwo differenzierbar. Und so konstruiert man solche Funktionen auch. Man nimmt einfach eine Funktion, die eigentlich nur aus Knickstellen besteht und lässt die Anzahl der Knickstellen gegen unendlich laufen und dann sieht sie eben am Ende so aus. Ja? Okay. So, this is one property of the path of the Wiener process. And the Wiener process is actually a special case of the so-called diffusion process, which I think I just explained is a model from mathematical physics to describe the diffusion of materials in another material. What is a diffusion process? A diffusion process is again a continuous stochastic process, and we call it a diffusion process if it fulfills the following characteristics. The first characteristic is the so-called Markov property, the Markov characteristic. What does it mean? The probability xt smaller or equal than xt under the condition that you know xu and you have information on the process at previous points in time is the probability of xt for s smaller than t. And even if you don't exactly understand this mathematical definition, you should remember that the Markov property of anything in stochastics always means that a process, a random variable, whatever, doesn't have a memory. What does it mean? It is of no use to us to know what the process looked like 1 day ago, 2 days ago, 5 days ago. The only thing that matters is today. And this is also a property that is relevant in financial mathematics when it comes to arbitrage property, arbitrage free markets, and fair games. Because it's the same with, for example, playing roulette. If you play roulette, it doesn't make a difference whether the last result was a 5 or an 8. A new game, and all things changed, and you don't care about what the last result was. This is for an example of a fair game, and also this is important for arbitrage-free markets. And this is the Markov property. It doesn't have a memory. Some things do have a memory. For example, the autoregressive process of order 1. This one does not fulfill the Markov property. Why? Because obviously it is important to know what the process looked like yesterday, 2 days ago, 3 days ago, because if you know these values, you can infer what the process should look like today. If you take xt, you multiply it with 110% and just wiggle it around a little bit, and you do this for 3 days, you still know, well, the process should be somewhere near xt, at xt plus 3. So this is a Markov property. Then the second property is probability of xt minus xs larger than epsilon is O of t minus s, meaning that large increments within short time periods only occur with a small probability, so this goes to 0. The third property is the mean of xt minus xs, conditional on xs, is mu of s and x times t minus s, and also below you can see a property for the variance. I don't actually very like these definitions. There are better ways to describe a diffusion process, and we'll see this on the next slides. Those are some more general properties that are more general than the Wiener process. But again, you can see you have a drift and a volatility function, and more or less the diffusion process is a generalization of the Wiener process with the mean drift and the diffusion being functions and not being constant. So this is the main difference between the two. So you can see that the Wiener process is just a special case with the drift function and the diffusion function being constant. So this is the main difference. The diffusion process has a varying drift and it has a varying volatility. And as you can see, drift and volatility and diffusion depend on the time and the process itself. So this makes it more complex and more difficult. In case we have a constant drift and constant diffusion, it's a Wiener process, it's a Brownian motion. Okay. Now, if you look at the bottom of the page, you can see the lemma of Ito. Does anyone has ever heard about the lemma of Ito and the central result in stochastic calculus? Never ever. Okay. This is something that is I always complain about this, and I even explain to the students now in the bachelor's degree, because I think this is very important to know when it comes to option price. So far we've talked about xt being a model for the stock price. This makes sense. But if we assume the stock price xt to follow a Brownian motion, we might also be interested in something else, in a function of t and xt. Now, what could that be? Obviously, a financial derivative. Why? The price of the derivative is a function of the point time, t in time, and the price of the underlying. So ftxt is usually a derivative price, for example, an option price. And if we assume a Brownian motion, or generally a diffusion process, the lemma of Ito, we don't have to prove it, but the result is quite magnificent. If xt is a diffusion process and some certain regularity conditions are fulfilled, we don't care about these. If xt is a diffusion process, then the lemma of Ito tells you that a function in time and the process xt is again a diffusion process. And what changes is we have a slightly different drift and a slightly different volatility and diffusion, but it's still a diffusion process. So if, for example, you assume a Brownian motion, it stays a Brownian motion. You simply have to take the drift and the diffusion and you have to change those parameters and you get again a Brownian motion. This does not seem like much, but this is the pivotal point in the proof of the Black-Scholes-Merton model. This is the most important ingredient you need to show that actually you can, with some very simple assumptions, you can derive an option price. And this was worth a Nobel Prize. So you take the lemma of Ito and you see that the new drift and the new volatility are actually given by the partial derivative of this function with regard to x plus the partial derivative with regard to t plus 1/2 the second partial derivative with respect to x. Now, does anyone know what these partial derivatives are? And the volatility, again, the partial derivative with respect to x. What is f? F is the option price. So it's the partial derivative of the option price with regard to x and t. And these are Yeah, these are the Greeks. The first one is the option delta, the second one is the option theta, and then it's the option, not beta, that's the option second derivative. Oh?
Yeah.
No, I think rho is with regard to the risk-free rate. I have to look that up. Option, what do we have? Rho, delta, vega. Yeah, I have to look that up. I don't remember. It's not rho. Rho is the partial derivative with regard to R, the risk-free rate. No? But in general, these are the Greeks. And here you can see why they are important. Yeah, they don't just give you the sensitivities of the option price with regard to the model parameters, but actually they are important in the proof of the Black-Scholes-Merton model. Okay, so we need this. So let xt be a diffusion process with drift mu being a function of t and xt, and diffusion sigma squared being a function of t and xt. So this is not a multiplication, this is not a product, but these are two functions. Mu depends on t and xt, and sigma squared might depend on t and xt. Then the diffusion process can also be written as a stochastic differential equation. Now this is tricky. Remember that we had an equation xt equal to w0 plus mu times t plus square root of t times the standard normal distribution. This is an explicit way of writing this process. A different way of writing the process is not to define it by xt is equal to. A different way is simply to write it like this. The changes in xt are given by the drift times the change in time plus the diffusion times the change in a Wiener process, in a standard Wiener process. Why is it a differential, stochastic differential equation? First of all, does everyone still remember what a differential equation is? A differential equation is an equation in which you have differential quotients, derivatives in it. And for example, this is a very simple differential equation. A different way of writing this is the derivative of y is equal to y. Now, first of all, we have to remember what is the solution of a differential equation. It's not a number, it's an equation, it's a function. Equation is a function. We are looking for a function f that fulfills this requirement that its derivative is equal to the function itself. Do you have an example? I always come up with two examples. First example is
the power of x.
The exponential function. Yeah? Exponential function. Why? If you take the derivative, it's again the exponential function. Second trivial example. 0. Function that is constant to 0. If you take the first derivative of 0, it's 0. So f derivative is equal to f. And you can see the differential equation has usually more than one. It usually has infinite solutions. So what do we need? We need an additional requirement, an additional property, and we usually either set or we fix the starting value or the final value. And if, for example, we require f of 0 is equal to 1, this means that now the solution is the exponential function. And this is a differential equation. If this function included any stochastic variable, any random variable, it would not be a differential equation, in German gewöhnliche Differentialgleichung, but it would be a stochastic differential equation. And this down here is an example of a stochastic differential equation. The process is defined by this differential equation. It's an equation in which we have differentials, derivatives more or less, and random variables. Wt is of course random, it's stochastic. And you should always let's go back one step. In stochastic calculus, stochastische Analysis, mathematicians, math students will spend the whole semester just working on the mechanics of calculating those differential equations, how you can form integrals, how you can differentiate, and how you can calculate the differential equation, and so on. We don't actually need to care about this. The only thing you need to remember is that if you were to interpret this differential equation, this means that this is a process that is defined by the property that changes in the process are given by a drift function times a deterministic change in time plus a diffusion parameter times a standard Wiener process. So we are using the Wiener process and we make it a little bit more flexible. We don't just take a Wiener process that can wiggle around a little, but we make it a little bit more complex by using a drift function and a diffusion function. And this is a stochastic differential equation and a stochastic process. Okay. Now let's talk a little bit about stochastic integration and the Ito integral. We again take a stochastic process, xt, and a Wiener process. And we now want to determine this stochastic integral. We want to calculate the integral of xt with regard to the standard Wiener process over an interval of a to b. This is actually quite difficult at first sight. If we were to simplify this and simply fix an observation omega, and we were to integrate x for a fixed observation omega with regard to wt, and simply use the corresponding Riemann-Stieltjes integral, this is in this case not possible. What does it mean? You probably know how the ordinary Riemann integral works. Has any one of you ever seen a Riemann-Stieltjes integral? Probably not. It's something you do in mathematics and probability theory. Now assume this is a function, and you know that the Riemann integral is just the limit of the fields you put below the function, and you let those Riemann not squares, quadrate of those spaces. You simply take them and you decrease the size of them up until infinity, and the sum of all those spaces then is the integral. In German, you might remember that das Integral, das Riemann-Integral, das Sie auch in der Schule kennen, ist einfach der Grenzwert der Riemannschen Summen, der Riemann-Flächen. Sie nehmen die Rechtecke, Sie lassen die Rechtecke immer kleiner werden und dann berechnen Sie die Flächen der Riemann-Rechtecke und die Riemannsche Summe und dann haben Sie das Integral. Ja? It's quite simple. Rectangles. Right, thanks. Yeah? So the ordinary Riemann integral is the sum of the rectangles when the size of the rectangles goes to 0. Okay. And the number goes to 0. Now, what is a Riemann-Stieltjes integral? It's a generalization. Now, remember that the Riemann integral is written like this. You integrate over x fx times dx. And in school, you probably have never learned why you have to include this dx. And there is a simple reason. Because in probability theory, in measure theory, you generalize this idea. You generalize it in the following way. You just say you have the function But you also take a weight factor, a weight function, and this weight function assigns weights to the corners of those rectangles. And for example, let's make it very simple. Let's say this is 1, this is 2, and this is 3. And we only look at 2 of these rectangles. 1, and let's assume we do this second one. Now the integral with dx would be just the length of one side, 1, 2 minus 1, times the length of the second side, f a minus f at b, for example. And in fact, this is already the special case, because we are simply taking the length on the x-axis as the weight for one side of this rectangle. But you can generalize it and you can say, I'm not using 2 minus 1 here, I'm using lambda, a different function of 2 minus lambda of 1. And this is the weight I'm assigning to this side of the rectangle. And then you can see that you have a function with respect you are integrating, and you wouldn't write dx, you would write d lambda. And now you are not integrating with respect to the, I think it's, if I remember it correctly, dx, the ordinary differences on the x-axis, this is the Borel measure. In mathematics, I have a special name. But you're not using just the distances on the x-axis, but you're using a weight function lambda. And then you can generalize the idea of integration. You can integrate with respect to almost any function. And you can integrate f with regards and with respect to a different function, dg of x, for example. No? And this is what happens here. You're integrating x, but you're not integrating with respect to the Borel measure, but you're integrating with respect to the Wiener process. You're taking just the points on the x-axis, and you're not using the distance between x and x2, you are using those distances and inserting it into the Wiener process first. And in probability theory, this makes sense because you're not using the points on the x-axis, but you're actually using probabilities with which you want to weight those rectangles. And this generalization is the Riemann-Stieltjes integral. So, as a special case, you get the Riemann integral. This is why it's called Riemann-Stieltjes. The first idea was by Riemann. He just took the Borel measure, and the generalization is due to Riemann-Stieltjes. And you can now integrate with respect to any measurable function. And then, in the end, you get this here. Yeah? You can see that you are using those function values as the length of the side of the rectangles you're using for your integral. Unfortunately, in this case, it doesn't work. But this could have been one idea. And this is due to the fact that the integrator here is not of limited variation. What is limited variation? It simply means that if you take two differences, or the difference of 2 points of a function, for example, you compare f at 5 minus f at 3, those differences between 2 points is not finite. And this is quite simple. It means limited variation. That if you have 2 points of a function, you take the difference, and this difference is infinite. It is of infinite variation. And the path of the Wiener process is, these paths are nowhere differentiable, so this property is not given. However, limited variation is given in the quadratic mean, im quadratischen Mittel. You don't have to remember this, but what one can do is, you can take the interval of 0 up to t, you divide it, and then you do the following. You look at the following Riemann-Stieltjes sums, the same idea with the Riemann sums. You want to integrate this function. You want to integrate the process. So you take, for example, x here and so on. And then you weight them not with x1 minus x0, but you are first inserting it into the Wiener process. Just the idea I described to you, that you generalize the Riemann sums. And then the limit of the Riemann-Stieltjes sums will be the so-called Ito integral, and you get an integral. And in the end, remember that dxt is a differential equation. And to solve this, you have to integrate. And integration in this case would mean xt plus s minus xt is equal to the integral from s to t plus s of mu du plus another integral. And again, you get the same result, that either you write out the difference here, xt plus s minus xt, between 2 points that are not completely adjacent, then you get 2 integrals, the sum of 2 integrals, or you get this more informal notation. You simply write an infinitely small increment, dxt is equal to mu dt plus sigma dwt. And this is what you usually will remember about the diffusion process. This is simply the lemma of Ito, written as a stochastic differential equation. You can see yt is the function in t and xt, and dyt, the change in the option price, in the derivative price, is given by this new drift times dt plus this new diffusion times the Wiener process. So it's again a diffusion process. Okay. Now we've seen a Brownian motion. Let's now generalize it, and let's look at a geometric Brownian motion. The stochastic process, we are now writing it as ST for stock price. Stock price follows a geometric Brownian motion if the following holds. ST is equal to ST0 times exponential function mu minus 1/2 sigma squared times t minus t0 plus sigma times the increment in a Wiener process. This is an explicit expression, but you can also write it in a differential notation. The change in the stock price is given by constant mu times st times dt plus sigma st dwt. What is the difference in comparison to a Brownian motion? The difference is that you now have the process itself in here and in here. If we write m equal to mu minus sigma squared over 2, this implies that the change in the logarithmic stock price is given by m dt plus sigma dwt. And m describes the momentarily continuous time mean return, and mu is the current mean discrete return. Now, what can you see here? Why is it important to look at d ln st? What can you see in this last line? It's the change in the logarithmic stock price, and that is, in discrete time, it would be log return. stetige Rendite. And I think this is quite interesting because there are so many discussions, especially in German literature, on the question why one should use a discrete return, why one should use a continuous return, stetige, discrete Rendite. And actually, I don't think this was much of a discussion because in many models like this, for option pricing, and this is just about option pricing, you need continuous processes, continuous stochastic processes. And in the end, it's quite natural that if you assume a certain process for the stock prices, you will get a very simple result for the continuous log returns. And what does it mean? The log return follows a random walk, Brownian motion. Yeah, this is a Brownian motion again. So you have to remember this, and I inserted an additional slide in contrast to this slide is new compared to the German script. You have to remember this. You usually assume the stock prices to follow a geometric Brownian motion. Now if you assume a geometric Brownian motion, the changes in stock prices satisfy dst equal to mu st dt plus sigma st dwt. Then the log returns of the stock follow a Brownian motion or a random walk. Remember that in discrete time, d ln st would simply be ln st minus 1. This is the log return. And as a result, you assume a geometric Brownian motion for the stock prices, you get a Brownian motion for the log returns, and in return, as a byproduct, the log returns are normally distributed, and the stock prices are log normally distributed. And this makes me mad every time I look at a German textbook, especially on risk management, because at some point, most German colleagues always argue, and then you assume a normal distribution for the log returns. And this is not correct. The assumption is made much earlier. The assumption you make is that the stock prices follow a geometric Brownian motion. And this makes sense because we have seen that even stock prices resemble a Brownian motion, and a geometric Brownian motion is even more flexible. So you don't assume a normal distribution. You assume a geometric Brownian motion for your stock prices, and you can explain that, and you can how do you say that in English? I lost my train of thought there. You can. I always want to say satisfying. No, you can. Justify, not satisfy. Right. You justify that theoretically. Thanks. But you don't assume a normal distribution. The normal distribution of log returns is more or less collateral damage of the assumption of a geometric Brownian motion for the stock prices. Now, if we look at a relative change here, it's delta S over S. It's St plus delta T over St minus 1 over a time period. This quotient is, again, log normally distributed. Because of the log normal distribution of St, I still have to correct those slides for errors. And the result is delta S over S is the exponential function of m delta t plus sigma square root of delta t times z, with z again being a standard normal distribution. So you can easily simulate from a geometric Brownian motion again. Now if you use the log normal distribution of delta S over S and try to approximate dst over st, the differential equation, by this Euler approximation scheme. Delta S over S, mu delta t plus sigma square root of delta t times z. This is not correct. At least not exactly correct. So this would be a simple way. Remember, dsd over sd is the relative change in continuous time. So the change is infinitely small, in an infinitely small change of time. Now, if we just use this stochastic process and just play dumb and assume, oh, we are now using it for a change of time from today until tomorrow in discrete time, and simply use mu dt is delta t, 2 days, plus sigma, and we know the standard Wiener process is just square root of delta t times a standard normal distribution. So if you just substitute all those parameters with its discrete counterparts, this is called the Euler approximation scheme, and it's not formally correct. It's not exactly. Now, we define the log returns being ln st over st minus 1. These are IID normally distributed. We've seen this before. And this is a byproduct of this. And we can then simulate the geometric Brownian motion by using a starting point S0 times exponential function of u1, and u1 being a simulation from a normal distribution. And then EU1 times EU2, and so on, and when we can simulate a geometric Brownian motion. Now, next, at some point, financial economists realized that actually even the geometric Brownian motion is not flexible enough to describe the time evolution and the dynamic behavior of certain asset prices. So for this, someone came up with actually those two people, Ornstein-Uhlenbeck. We take an Ornstein-Uhlenbeck process, which is the simplest example of a mean reverting drift, meaning that the mean reverts and the drift reverts to its mean. So if you have a period of time in which the drift is going up, it will go down afterwards. This is meant by mean reversion. So the stochastic process, the Ornstein-Uhlenbeck process, is given by alpha times mu minus xt dt plus sigma dwt. And the Ornstein-Uhlenbeck process is especially used in the Wasicek yield curve model. And there it plays a role for interest rates. Now, there is some mathematics here. I would say just leave it out. You can see that there are some properties. For example, you can write it in this way. The Ornstein-Uhlenbeck process is a Gaussian process that is all xt are normally distributed. It's a very simple process. You simply need to remember that the Ornstein-Uhlenbeck process is given by this equation, and it's mean reverting. And you can see that the mean goes back and the drift goes back. So, negative values of xt are possible, and this is one reason why, or even though it's used in some interest rate models, this is actually not the best model, because interest rates usually are not net. Usually. So you can see that the expected value of xt is mu, and constantly mu, even though the drift might not be constantly mu. The variance is sigma squared over 2 alpha. Therefore, the parameter mu corresponds to the long-term mean of the process, and this means that increases of the Ornstein-Uhlenbeck process are not stochastically independent. But again, the drift will revert to the constant parameter mu after some time. This is mean reversion. Yeah? Even though the drift might be higher or might be lower, after some time it will revert to the long-term mean mu. Then you can estimate the parameters, for example, alpha hat, a hat, mu hat, sigma hat, and you can do this, and this is the Ornstein-Uhlenbeck process. There are also so-called root diffusion or square root processes, and one example is the constant elasticity of variance, CEV process. It is defined by mu xt dt, that's the same as in the diffusion process, but now sigma square root of xt dwt. And here it holds that the conditional mean is given by this, and the process now has the property that the expected relative squared change over a small future period is proportional to the inverse of the current value of the stochastic process. Actually, one doesn't really need this to remember. If you ever come by a model that uses a square root process or the CE process, simply look it up and remember that this is a very special type of a stochastic process with some special properties, which is needed in some cases, especially when you want to model interest rates, default probabilities. The same with the Cox-Ingersoll-Ross process. Here you can see that it's also mean reverting, and dxt is equal to alpha mu minus xt dt plus sigma square root of xt dwt. So again, you can see you're combining the properties of the Ornstein-Uhlenbeck process, mean reversion, and this this property here that high results of this process and high values are connected and related to low volatility, and you get this process, the CIR, the Cox-Ingersoll-Ross process. I'm not too crazy about these processes, and you can look at these. I'm more interested in the next processes, and you might have a look at these in more detail. For example, first of all, you can take the geometric Brownian motion and you can define a multivariate version of it, and you get a multivariate geometric Brownian motion. This one's interesting. And in the next chapter, we'll look at jump processes. What is that? Look at it in the following way. We start with Brownian motion, a very simple model that is more or less just the process of a standard normal distribution that can change a little bit over time. Then we have a geometric Brownian motion, which gets a Cox-Ingersoll-Ross, a diffusion process, and it gets more complex and more flexible from model to model. Now, one empirical property is very important, and asset prices usually possess the property that volatility doesn't change gradually, but it suddenly increases a lot or decreases a lot. And this is the property we are trying to model with the jump processes. Jump meaning it's a process in which volatility can suddenly jump and increase by a lot. And this is what we need to model, and you can see here what the process looks like. For example, a Poisson process, and then we have some properties, and we have a very large MATLAB process. For example, here you can see a Poisson process with intensity 2, and in the end, this is a geometric Brownian motion, and here we have a jump diffusion process. We get the geometric Brownian motion, and we use dst mu st dt plus sigma st dwt. So this is the geometric Brownian motion, and now we also get plus st djt, and djt is a Poisson process. It's an aggregated Poisson process, and afterwards you see that actually these are two jump diffusion processes. And for example, here you can see that at some points, here for example, volatility slightly appears to be higher than before. And this is also one of the most, well, I wouldn't say it's the most sophisticated model, but jump diffusion processes are way up high on the ladder of complex asset pricing models. And just to stop here, if you ever wondered what financial engineers, quants, and financial mathematicians do all the time, even today in research, if you take Brownian motion and you use the lemma of Ito, you will get a very, very simple result in the Black-Scholes-Merton model. You will get the formula you might have seen before and you've learned in other lectures. Yeah? The price of a European coal auction that doesn't pay out dividends is blah, blah, blah. It's the analytical solution of this setting with a Brownian motion. Now, in case you have a more complex derivative or you are using a more complex asset pricing model, for example, a jump diffusion process, you will have no analytical result and you need to use a computer and you need to use state-of-the-art mathematics to come up with a solution for the option price. And this is what computational finance in the end is all about. Computational finance is often synonymous with just this type of work, coming up with new models, more sophisticated, more flexible models for asset prices, putting it into the Black-Scholes-Merton model, and trying to find good solutions in finite time with finite computer resources for the option price. Because it's all about flexibility here. A better model for the option price, for the underlying prices, and more complex and more non-standard derivatives. So plain vanilla and Brownian motion, that's simple, but as soon as you have exotic options and more complex processes, you will get into trouble, mathematically speaking, and then you need the computer. Okay, we'll talk about that next week. If you have no questions, then let's stop here with the geometric Brownian motion and continue here next week. Thank you.